Good morning. This is Jim Chastain with EasyPower. We've had requests to demonstrate dynamic stability in this slot, which we use for refresher updates. And as much as we can cram into 30 minutes, this is it. So welcome, and I'll be able to answer questions at the end of the session. So I appreciate everyone from joining. One of the obvious side benefits of conducting an arc flash study is the fact that the database that we have built is the ideal representation of our electrical distribution system. That means we can take the data and produce a PowerFlow or load flow study relatively efficiently. The load flow is the result of the simultaneous solutions of the DC and AC equations of the elements in the system, and because they affect each other, this requires an iterative process which makes it ideal for a computer application. Very frequently when we do a arc flash study and a customer has the ability to record or take down the voltage and current readings in certain parts of the system, we will do a load flow study, at least a partial one, as a means of error correction or verifying that the data collection process was as accurate as possible. And when we talk about stability, that infers that our system has the ability to find a new steady state condition after we've made changes or stimulus. So the system is designed to find a new equilibrium. So dynamic stability is the analysis of this ability to predict system reactions to any given change or stimulus. To properly predict the system response, we need to include something called the full flux model in the elements which have interactive magnetic fields and which will be affected by the changes in current or voltage. So as we start with the database model, you'll see that although it's developed for the arc flash, it basically provides a network that we can then add or make the variable elements enhanced, and then our program can calculate the new PowerFlow solutions at a given change in time. Typically, and we can control these, but typically the smallest increment would be about a half cycle between steps. What this boils down to is that we have a network which is inside of this cloud, and although there's certain elements inside of this that respond to changes in the system, they are really not the drivers of the change in current and voltage. So you'll see that relays, fuses, protective devices, even transformers may be affected by the change, but the elements that are interactive and are most influential in what the change in the PowerFlow solution will be the motors and the generators. Now you'll see when we get into the actual EasyPower tools, most of the elements have a stability tab, and we'll talk about what that means. And obviously the more data we have on the system, the more accurate we can make our resulting solution. Now the way the data entry works is if we have the specific data sheets on, let's say, a motor, then we have access to many of these parameters that are required for the full flux model. If we don't, the tool actually includes a library, and you'll see this. There's a generic listing for different sizes of motors, and then there's a couple of library elements that include specific manufacturers. And then if you still need more accurate information and you have access to the torque charts for the motor, you can actually digitize these and include them in the model. So you'll see that there's the need to include the motor model itself and then its characteristics for starting and running. Now when we get to generators, it's a little bit more of a complex situation, because in addition to the basic model for the generator itself, there's also a need to model its excitation system, the governor system, and the feedback elements. And so you'll see that those are, and this ends up being a little bit more of a complicated tuning situation. And frankly, we have engineers on site that are expert at this and can be very valuable resources if you're doing a dynamic stability study. Just doing the study would not be that useful if we weren't able to display the results or the parameters that we're looking for. So built into the dynamic stability tool is the ability to customize a number of plots which can virtually monitor all voltage and all system elements that have potentially voltage or current within them, and in the case of generators and motors, even more valuable data than just voltage and current. You'll see that in some of the examples. The tool also has the ability to respond to different types of operator inputs. For instance, there's a double-click stimulus which allows me to open or close certain breakers or contactors, and as I do that, the system knows expects that I need certain results. And so there's an auto display feature that if there's a motor in the circuit, then I display the motor properties. If there's some other element in the circuit, then it will display properties that are valuable for that particular function. And then finally, there's the ability to develop scripts which will set up certain parameters and then invoke a stimulus, and we can plot even remote reactions on different parts of the system as we do this. So without all that verbiage, it's probably worthwhile getting in and talking about this. The system starts as we launch the dynamic stability tools. It starts with the solved PowerFlow result. And the point here is we need this to be a quiescent point, because if the system is moving before there's any stimulus or the response is changing, then there's really not much value in trying to provide a what-if scenario. So for starters, we need to have a valid or valuable PowerFlow result. So I mentioned the double-click response and the scripts that can be set up. The nice thing about this is that this is not a text base. It's literally just a pull down and choice of parameters, and we'll see this as we get into some of the examples. Again, the double click allows us to change any of the elements in the system that may be able to open or close, and then the system anticipates what we're expecting to see out of this. And then a third window frame is included in the tool, which is essentially the event log, and this will display system element changes that we may or may not be aware of, and this again can both help us improve the simulation that we're trying to accomplish, but also make sure that we are aware of other elements in the system that may be changing that we didn't know about. So anyway, these are what we're going to be trying to demonstrate in our examples. The first example is going to be a cogen plant, and the question is, how quickly can our cogenerator respond and pick up loads if we lose the main utility supply? So what we've developed is a load shedding script, which has frequency relays, or relays that respond to specific set points of frequency, and as the frequency drops, then we're going to shed or disable certain feeders such that there's less load on the cogeneration generator, and see how quickly it can respond to the frequency, restoring the frequency to 60 hertz. So again, this would be valuable both in tuning the response time of the cogeneration, but also setting up the critical load arrangement if we're worried about losing utility power. The second example is going to be a medical clinic example. Basically, this is a redundant system, or a medical center that has a redundant system, an emergency backup generator. And the question is, if we do have a fault or a loss of power from the utilities, will the emergency generator be able to sustain the elevator system if everybody were to jump into the elevators at one time and press the button? So we're going to show the setup of scripts to be able to demonstrate that. And then finally, we're going to have an example where we have a steel mill that uses some very large fan motors for evacuation of fumes and whatnot. And when we start that fan, it actually kicks up the total current for the plant by over 100%, and that starting cycle lasts 15 seconds, which makes the whole plant susceptible to any other load starting. So the question is, how do we tune the soft start to keep that excursion as small as possible? So let me see, looks like we got questions starting already, and we'll answer these when we get to the tail end. So let's kind of jump into this. All right. Now the EasyPower tool, as I mentioned earlier, allows us to take a lot of data, whether it's necessary for the arc flash studies or not. So here we have a system that was developed for an arc flash study, but the plant, in addition to a utility supply and a cogeneration supply, has frequency sensitive relays. And in this case, if I click on the relay icon and not the, they're all set for different frequency trip points. So this first relay is set for a frequency setting of 59.5 and a delay of 1/10 of a second. So 1/10 of a second after the frequency drops below 59.5, this relay will drop out the loads that are in this particular feeder. Likewise, this relay is set for 59 and then 57.5. So ideally, is if we pull the plug on the utility, we would like to see the response of the cogeneration pick up the loads, so we lose a minimum amount of our total system load. So we go into stability focus, and you notice we have the 3 frames. Again, on the left is the one-line diagram that has already an existing PowerFlow solution, and this is resolved, showing us what the typical display for a load flow or a PowerFlow study would be. As I mentioned earlier, we have the ability to double-click on a system. So here's a fairly large load. Let's open and resolve, and then double-click on this. And as I do that, I've started this motor, and the tools automatically know that what I'm looking at is a motor. So my display, we're showing the motor voltage, motor current, motor speed, and then the torque that's being generated by the motor. And this gives us a pretty good idea of the response of that motor. I didn't talk about the data. In fact, we'll do that when we get into the next example, how the data is entered and what it looks like on these particular devices. All right, let me go back and close. So now what we want to do is use one of the scripts that's been developed. And here now, we're going to effectively pull the plug on the utility system and then see what the response is on the utility breaker and see what the response is for the rest of these loads. And I'll get into what the script looks like in a second. So now as we run this simulation, all right, plot 1, we're looking at the cogeneration parameters itself. And we see first display is the speed, then the voltage, the current, the cogeneration angle, and then the bus frequency. This last trace down here is the bus frequency, and we can see at 1 second things were fine, and that's when the utility breaker was pulled. Frequency immediately drops, and now it's at 59.8. As soon as it gets to 59.5, we'd expect to see a response from the relay, and then a tenth of a second later, the relay will open. During this time, we can see the voltage and the current on the cogenerations dropping. There's an immediate response to the decrease in voltage as the generator starts to try to pick up the load. At this point, it's hit 59.5 and we've dropped off some load, and then gradually the cogeneration starts to pick up the voltage and the speed and the frequency, and it survives the loss of the other two legs. Now so that's what we see here as a result. The first relay tripped and dropped off this particular feeder system, and then the balance of the system was able to maintain. If we give a quick check of the log, we'll see exactly that's what happened, is that we initialized the system. We're having some settling results. Then we open the device here at 1 second, and then we can see R1, which is actually the relay in line with our cogeneration. It picks up on overcurrent, and then at the same time, or actually half a second later, we see the frequency relay drop or pick up at 59.5, and that trips on a tenth of a second later, and then we see that the relay R1, which is our overcurrent relay, starts to reset at 1.92 seconds. So this gives us a step-by-step, and frankly I wasn't expecting the overcurrent relay to trip whenever we went into this exercise, but now that you think about it, that's pretty much what we're talking about, is an overcurrent condition until the generator recovers. All right, so that's an example one. Let's go to the next example, which I think was my medical system. And here, again, the goal was to verify or understand the conditions that our generator, our elevator controls would continue to work, even though they were only being supplied along with the critical mission systems by the standby generator. So we've got our two utility supplies that are isolated. If we get a hard fault or a bus fault that isolates the system and causes the ATS to switch over to the standby generator, then we're going to verify what starting conditions we can survive in terms of these three motor controllers starting at the same time. So to do this, before I do that, I want to go back and look at the data entry. So you'll notice that for these motors, we have a different icon compared to what the motor icon is for a standard element. All right, the standard element just has a little M inside and allows us to go in and put in the horsepower and the short circuit X over R and the TCC limits. What we're talking about here, though, is motors that have the stability tabs populated, and as we go to the stability tab, we see that we've enabled the motor model. We've selected a Rockwell motor that's close to what the size of these motors have been, although it looks like I may have played with this one. But once we pull that in from the library, then that populates our list of parameters that control the full flux model of the motor. In the case of starting, we're going to use a generic speed squared, and likewise for the motor running. So these are just linear functions. And once these are all populated, then that's what the system used for the simulation. Now I mentioned if we don't have something close in the library, and we do have the torque speed curve, the tool allows us to actually go in and digitize based upon matching this drawing tool with the curve that we've pulled in a PDF format, and then it will translate this data into parameters that will correspond to what's needed by the model. All right, so the next thing we're going to do is go into stability. We're going to look at the scripts that we've done. First of all, steady state is pretty much what we're looking at as far as the power load flow study. We're going to go in and let's go in a staggered start. What we've done here is we run the system for 1 second, then we fault the bus, which is this main bus a little where the utility comes in. We give the system some time for the standby generator to come on and the ATS to flip over. Then we change the motor parameters and turn the motors on, and then we separate it by enough time that we know that there's no interaction between the motor controllers. Then the next partial overlap will separate by a smaller time element, only a half a second difference, so there's some partial overlap. And then finally we'll start everything at the same time. So let's see what this looks like. If I pick out each one of these scripts and then run it. And what we're seeing here now is we've plotted the bus voltage and current on the C23, which is this system right bus 17. All right, and so you can see with our extended time separation, we don't have any problems bringing each of the motors up to speed. So let's reset that, try the partial overlap, run it. Right, it looks a little ragged, but apparently the motor start survives. All these motors are still online at the end of the system, at the end of the exercise. We see our ATS is transferred over and our generator is up and running. So let's try the third example where we start everything at one time. And we call that one full overlap. And as we start it here, now we can see that the motor starts didn't survive, that at the end of the cycle everything is offline. The ATS transfers successfully. The standby generator is still online. We don't know exactly the mechanism that caused the closure or the failure, but we can go through and look at specifically. It's just our contactors dropping out of the motor starters because they didn't have adequate current from the bus to be able to sustain the motor start. Okay, nice exercise, not necessarily for facilities, but for people that design motor controllers. The third example we're going to cover is probably something that happens a little more frequently in large systems, and that is having a very large load that can overpower or at least threaten the starting system. Let's see, need to talk and click at one time. One large load or a couple large loads that can threaten to swamp out the capabilities of the whole system. So here we have a large load fan, a 1500 horsepower motor that as we start, you'll see that it doubles the motor, the current draw for the whole plant. So again, we're going to close this particular breaker and see what happens with the double click. All right, because the system knows I'm looking at a motor, it gives me the voltage, the current, the kilowatts, and the kilovars. Now I've also plotted, if I go in and plot a specific part of the plant, I've picked up on plot 6 here that I want to look at the bus voltage at the main breaker and the current that's being drawn by the whole plant. So as I go to look at plot 6, I can see now my current goes from 197 amps to over 450 amps, and it maintains that for about 14 to 15 seconds. So during this time, because this is very close to the set point of the breaker for the whole plant, the overload relay, I'm at risk of bringing down the whole system. In fact, if I come back and look at this, yeah, I don't see that we have any. Well, you can see right here, the main breaker gets up to one at 21.98% of travel, and the other at 40% of travel. And so I'm well on my way to actually losing the whole plant if something goes wrong with that starting cycle. All right, what I want to do is go in and look at a script. What I want to do is basically set up and control my soft start parameters. And in this particular case, let's see if we can call them trial 1 and trial 2. We start off with a soft start at 40% and then step to 60% and separate those, and then go to 100%, separate those each by 10 seconds. And let's see what that does to my system. So trial 1, start. All right, so what I'm looking at here again is the voltage and the current at the main panel or main plant input. You can see I come up in stages. So now I'm starting at my 197 and I go to 300 and then to 357 and still up to 457, but that period lasts for, looks like about 7 or 8 seconds at the max. So I've limited my liability, but there's still some sensitivity. And so let's see what happens if I stretch that a little bit longer. Let's go to trial 2. And you can see that what we're setting here is I'm going to 70% voltage on the power start, 85%, and then 95%, and set those each at 15 seconds and see what happens. So let's see if that gives us any breathing room. Now again, these are somewhat artificial in that I haven't totally modeled the whole plant, but you can see that we're starting to get our desired result. Again, we're starting at 197 as far as the total current in the plant, and then we go to a max current of 386, 385, and then up to a little bit over 400, 420, and now this period lasts for 10 seconds. So there still needs to be some tweaking done, but the point is I have control, or I have the ability to kind of mitigate what's going on. If I go back and look at my motor, so this is specifically ends up being the fan current, the voltage, and then the RPM on the motor. You can see that the motor is drawing 1,300 amps, again at a different voltage than our main plant. We're getting the speed up to, looks like 850 RPM. We might want to take that higher. But again, we're able to go through some very valuable feedback and simulation of what the impact is on the rest of the plant by making variations with my soft start. Again, somewhat of an obvious application, but there's many other applications inside a plant of this nature that would have the same type of benefit. One point I would want to make, you can tell that as I look at my one-line diagram that I've only modified a few of the major loads in the system. And while that limits, let's see if I can find if I've got any other stability data on any other loads. I do not find one immediately. But that gives me the ability, here's where I was monitoring one of the impacts, because this is very heavily loaded MCC. It gives me the ability to go in and improve my model the more accurately I include or use the full flux model for the heavy loads. All right, that kind of finishes what I wanted to discuss on stability. Let's kind of go in and look at what we've found out. So dynamic stability can stimulate system response to a wide range of stimulus and measured responses, and it's this ability to simulate and prevent damage or go through what-if scenarios without having to use the full plant to run these simulations, which actually could take things offline. So in fact, we can save large sums of money by the simulation rather than taking a stab at the unknown and not knowing what to expect when we run the actual system. So for instance, the applications might be just exactly this, predicting the best settings and the effect of running soft start settings before we apply those to large loads. Tune the generator or the standby generator's response to system faults. And obviously it becomes an ideal environment in dynamic stability for answering questions like, well, if I were going to take this system and now add alternative energy sources, what's going to happen in my system? Appreciate everyone from attending. We will take questions here in a second. And I'd like to refer you to, if you'd like more information on dynamic stability, or if you'd like to be able to try the tool out, please contact sales@easypower.com, and we can help you with that discussion. There are a lot of other useful resources on the website. We have several sites announced for regional training. I invite you to go in and see what may be set up for locations near you, and anticipate registering because of the very deep technical training that's involved that you could benefit from. We also have the ability to offer engineering services basically as a backup for your efforts. We can do everything from just an engineering review of your particular file to doing parts of your study that for some reason you either don't have the bandwidth or the experience, and this could fall into the areas of say protective device coordination, load flow, or even dynamic stability. Appreciate everyone attending today and look forward to talking to everyone next week.